Fantastic. Right. Hi there. Hope you can all hear me well. My name is Stephen. I am one of the tutors here at Oxbridge. And today we've got another A-level geography YouTube live for us all. So if you missed the first one, that is no worries at all. It is up on the Oxbridge page. So it is in Unit 1. We did hydrology and fluvio-glacial morphology. Great topic, great title. Definitely worth checking that out if you haven't seen that already. Today, we're going to do a very similar thing. We are going to be looking at Unit 2, which is much more easy to say. It is our atmosphere and weather unit, okay? So we're going to do a very similar thing as we did last time. We're going to split the hour into about 4 sections that we've got here, 2.1 through to 2.4. And we're going to take a little dive into what this topic is all about and the main things we need to get out of it. Now, as with the last live that we did, the idea isn't really to teach all of this content. If we were going to do that, we would need much more than just 1 hour. We need a whole series of YouTube lives in order to actually do that effectively. So what I'm really trying to do in this hour is to give an overview of the unit, touch on some really key concepts, explain a couple of ideas, and point out some of the tricky areas, some places where you should perhaps focus some of your study a little bit more in order to get the most out of this unit. Alongside that, we're also going to do a few practice questions, so some exam questions from the CIAE exam board. So we're actually going to get some real life look at what you could be asked if you were to study this unit and then go on to sit the exam and answer the questions on it, okay? So first of all, we're going to have a look at the first part of the unit, which is diurnal energy budgets. As always, the chat is there. I can see it come up. If you've got a question, just pop it in and I'll happily answer. If I don't see it straight away, I'm going to pause at the end of each section and we'll go through some questions then as well. Okay, so if anything pops into your mind as you're watching or towards the end, we'll leave a little bit of time for some questions and Q&A as well. Fantastic. Right, so let's get started on our first little unit. So what the first part of this unit does is it looks at diurnal energy budgets, okay? So here we've got factors affecting the energy budget, things like incoming solar radiation and reflected solar radiation, the energy absorbed into the ground, albedo, and sensible heat transfer. We've also got long wave radiation, latent heat transfer, evaporation, dew, and absorbed energy returned to the Earth. Lots of keywords in there, lots of interesting things. Essentially, what this first part is looking at is how does the energy budget work? How does the atmosphere, how is it set up? And what are the energy transfers coming into and out of our atmosphere? So first of all, it's really important we remind ourselves of the different parts of the atmosphere. So we're divided up into different sections. Starting from the Earth's surface, moving out towards space, we have our troposphere, okay? So this is our lowest layer of the Earth. This is where the weather that we experience sits. So any weather forms, acts, and sits within the troposphere. It's where we have a lot of our water vapor, which leads to our jet streams, which we'll touch on a little bit later. And it's also the layer of the atmosphere that traps all of our greenhouse gases that affects global warming, things like CO2, methane, those sorts of emissions. Moving further outwards, we have our stratosphere, okay? Much calmer, much less going on here. It's essentially the layer that has the job of protecting us from our UV radiation, and kind of where you find the upper limit of modern aviation aircraft flying, okay? So that's sort of 30,000 feet limit. Beyond there, you start moving out a little bit more into kind of the space. You've got your mesosphere. So this is the coldest layer that we have of our atmosphere. Really, really windy. Sometimes up here, you can get those high wispy clouds that you see in the sky sometimes, but usually mostly invisible to the naked eye. And that just sits above our stratosphere. Also worth mentioning our ionosphere, not in the diagram, but this is an electrically charged region. Quite important because it reflects some of that solar wind coming in from the sun, and this is where we get our auroras. So our aurora borealis that was quite prominent across the northern hemisphere, particularly last year. That's where this will form. Okay. And then your outer region, this is your thermosphere. This is your largest layer. A few gases up here, mainly absorbs your UV radiations from the sun. Can get quite warm up there, so it's certainly not the coldest part just because it's further out. But that is our outer layer of our atmosphere. That's where our International Space Station lies. So worth being aware of those key terms as we go on to talk through them throughout the unit. So what is our energy budget? So this is a key term. This refers to the amount of energy entering a system, the amount leaving the system, and the transfer within the system. In simple terms, what energy is coming in from the sun, what energy is being reflected back by the Earth, and what's happening in the space where that's occurring. That's what we're essentially asking here. So what we're concerned about in incoming solar radiation is what happens to it. So all of that sunlight coming in that we can see in the diagram, about three things can happen to it. It can either be reflected by the clouds. So that incoming solar shortwave radiation gets reflected back to space. Some of it is reflected by gases. So again, things like CO2, methane, nitrous oxides within the Earth's atmosphere, they can reflect the radiation back. But the majority, about half, 51%, is absorbed by the Earth's surface. That's what warms up the planet. Now, we also have outgoing radiation. So this is some which is lost to space, okay? So it goes straight back out. Other outgoing radiation is lost with evaporation. So the heat needed for evaporation to occur, that uses energy. So that's where some of that energy goes. Some of it is absorbed as heat, and some of it is absorbed by our atmospheric gases. So again, that's CO2 and methane absorbing that radiation. Now, the Earth's solar energy depends on four different things, okay? It depends on the sun's energy output, okay? Solar, what we call a solar constant, so how much energy is the sun giving out? This can vary throughout the year. It can vary depending on the sun's activity. The Earth-Sun distance, so again, that varies across the year from summer, where it's closer, to winter, where it's further away. The angle of incidence or angle of sunlight. So again, remember, our Earth is on a 23-degree tilt. So that means that at the equator, they're getting more energy input. And at the poles, that same amount of energy is being spread out over a larger distance. And also the day length. The moment we're slightly shortening, we're heading towards our winter solstice, we're making our way towards that. But currently we've got really long days, we're absorbing more energy from the sun, we've got more going on, okay? So those are your four things that will affect our energy budget here. Now, we can have two different types of energy budgets that we talk about. And there's a lot of text on some of these slides purely so that when this is uploaded online, you can go back and look at it. Kind of provides a nice little summary of the notes that you're given through signing up with Oxbridge. Okay, so it's just a more concise revision sort of PowerPoint with that information in. So as I said, the diurnal energy budget can be talked about in two different ways, either daytime or nighttime. And we talk about the differences between what's happening during those different periods. So during the day, obviously, we've got 100% of our solar energy coming in because it's our daytime. That's being reflected by our clouds, our gases, and the Earth's surface, and about 51% of it is being absorbed by the Earth itself. The Earth can then re-radiate, in other words, bounce back some of that energy as what we call long-wave radiation. So it's always short wave when it comes in and long wave when it goes out. Some of that heat is lost through evaporation, as I've said. Some more of it is lost through sensible heat transfer, okay? This is a really weird term that trips so many people up, but it is on that spec that we saw at the start. Sensible heat transfer just replies to warm air turning into cool air. It's essentially your conduction, convection that you learn about in GCSE physics. That is sensible heat transfer. It's the changing of air temperature from warm to cool as it rises. Okay, so that's all we mean by that term, sensible heat transfer. Now, we've said that incoming solar radiation is reflected by certain things. This is what we call our albedo. Albedo just refers to the reflection of some of that incoming solar radiation. You talk about like the poles, Antarctica, the North Pole. They have a very high albedo because they're lovely white surfaces, which are really good reflectors, reflect a lot of that heat back into our atmosphere, either to be escaping or to be absorbed by some of our greenhouse gases. The Earth heats up as it receives this energy and re-radiates it as long-wave energy. As I'm saying, that's mostly absorbed by greenhouse gases, maintaining our planet's temperature. Latent heat transfer during evaporation, so that is the energy lost when you heat water and it evaporates into a gas. And that helps to cool down our atmosphere. Equally, when it condenses, that can warm up our atmosphere. We've talked about our solar energy. That can have an impact along with our day length, the distance from the Earth, and the incidence of the angle of the incoming radiation. And remember, we also have, because we get so much energy at the equator, we have a really high surplus, essentially, of heat and energy at the equator, which then spreads out along the Earth towards our poles. So from the equator towards our poles. So that's in daytime. That is everything that could be happening during our daytime energy budget. Thankfully, the nighttime is a lot simpler. We have, again, long-wave radiation being lost to space. So all of that heat that was absorbed during the daytime, that at night is re-radiated as long-wave energy going back out to space. And when we have lovely clear skies, that can just go straight out. When it happens, the heat is lost from the surface, and so the surface cools down quite rapidly. Again, if you have clouds, that's going to reduce the amount of heat loss. When that heat does disappear, again, that's through sensible heat transfer, so just going from warm to cold, we can often form dew. Okay, so this is when the water essentially condenses because it's got cooler, and that water forms on vegetation. That's all we mean by dew. So dew is just when water forms on vegetation due to that lower temperature at the surface of the Earth. So that is really what's happening in our nighttime energy budget. It's dominated by our emission of long-wave radiation. That is the main thing to know there. Fantastic. Right, so first look at some of our exam practice. So here we have a figure showing a simplified diagram of one part of the energy budget over land and sea. Using figure 2.1, calculate the value of energy at A in watts per meter squared. Name energy transfer B. And with reference to this figure, describe the path of incoming solar radiation for 4 marks. And also for 4 marks, explain why reflected solar radiation may vary over time. Now, obviously, you can't write an answer in the next minute, but just take the next 30 seconds to have a think of some of the factors that you might put into some of these answers. Have a look at that figure, and then I'm going to show you some model answers. So just take 30 seconds to have a look and think what you might write for an answer. Wonderful. Right, let's have a little look at some of our answers then. So first of all, calculate the value of energy at A. So all we need to do here is find how much energy is coming into the system, how much energy is being lost from the system as well. So we can see that we've got 185 watts per meter squared coming in. So that's taking out the radiation that's been reflected by the clouds, the radiation that's been absorbed by the atmosphere, and that's the amount of radiation coming down to our Earth's surface. Some of that is being reflected back up from the Earth's surface. So we were losing 25 watts per meter squared again. So 185 minus 25, at this point, we're going to have 160 watts per meter squared. Name transfer B, we've got reflected solar radiation. In these types of questions, you need to say where from. So the reflected solar radiation from the clouds. Okay, so that is what's occurring at B. Describe the path of incoming shortwave solar radiation. So here we want to be talking about the absorption by the atmosphere. So this is our incoming solar radiation. It's being absorbed by the atmosphere. So that's what's happening at this point in the figure. It's being reflected by the clouds. That's what's happening at this point in the figure. It's also being reflected by the surface of the Earth. That's the 25. And it's also being absorbed into the ground. Okay. These questions are not designed to trick you out. It even says refer to figure 2.1, which is fantastic because that means we get to use the information, use the figure, and use that in our answer. And finally, explain why reflected solar radiation may vary over time. It varies because of cloud cover changes, and that will affect how much sunlight can actually get to the Earth. Changes in the Earth's surface, such as snow melting or land use changes, that's going to affect our albedo, affecting how much light is reflected back into space as well. So those are two really big things. You could talk about it may vary over time in terms of year. So we might have different day lengths, different distances from the sun. We might also mention the sun's activity there. So sometimes it's more active, sometimes it's less. Hopefully that gives you a little view of some of the shorter answer questions that you might get on energy budgets. Fantastic. Right, moving on then. We have, I won't lie, probably my least favorite part of this topic. The global energy budget is really, really hard for most people to get a good sense of. We understand that weather, we understand our weather, we know what it is, we understand it has an impact, but understanding the specifics of how it works is really, really tricky. My honest advice is this 2.2 section of this unit should form a really large part of your study time. The human impact, weather processes and phenomena, they are slightly easier to understand. They are slightly less content in these last two sections. So my advice would be really try and get to grips with 2.2. There do seem to be a lot of exam questions that come from this part of the topic. So my advice, focus on 2.2, if anything, slightly more than 0.3 and 0.4. So here we're looking at essentially how does radiation occur across the globe? Where is the most amount of radiation coming in? Where is the least? What happens in our atmosphere because of that radiation? So what is our wind doing? What are our oceans doing? And how are they distributing the heat around the planet? And then it also looks at seasonal variations in temperature, pressure, and wind, and how this is influenced by your latitude, the distribution of land and sea, and our ocean currents. So quite a lot that intermingles to work in this unit. That's why it's so hard. There's so many intricacies of what's going on. So what I want to do is just give you an overview of where you should focus your attention so that moving forwards, you're on the right tracks. The genuine principle that we have with our global energy budgets is that most of our energy is coming in at the equator. It's the hottest part of the planet, we know that. It's because it receives the most direct sunlight, while the poles, they get the least direct sunlight because they are at the poles of our planet. And so the sunlight at the poles is spread out, the sunlight at the equator is concentrated. Now, naturally, just like the radiators in your home, heat moves from hot to cold. So we have this general transfer of heat from low in the middle, in the equator, towards our poles, where it cools down and then moves back towards our equator. Now, if we didn't have any oceans on this planet, if we were just a land-based planet, this is how our energy budget would work. The trouble is, we have continents that are funny shapes, funny sizes, spread all across the world, and we have huge oceans that disrupt this energy budget, which is why, in reality, it's not this simple. The concepts still apply, though. So at the equator, that warm air rises, and when the air rises, it forms low pressure. That air moves towards the poles where it sinks, forming high pressure. I always think of them as opposites. So if you're sinking, you've got high pressure, and if you're rising, you've got low pressure. They kind of work as opposite pairs. And that's what drives our convection, essentially convection currents, and our atmospheric circulation. Now, there are some really good Met Office YouTube videos that explain the circulation that we have. And they are linked in the Oxbridge notes, and I really highly recommend you watch them. There's one linked in the notes, and then you can, when you get on YouTube, you can see on the side, it's got loads more. They're all worth a watch about the 3 cells, about the global circulation, really, really good information in there. And it will detail for you our 3 cells. So because of our oceans and land masses, we have 3 cells rather than just one big one. We have our Hadley cell. This is what forms at the equator, okay? So we essentially take like a mirror and put it at the equator. You've got one Hadley cell on each side of the equator. Your Ferrel cells form next towards the poles, and your polar cells form at the poles of the planet. Okay, and these are our 3 global convection cells that determine our weather. So you need to know those 3 cells. You need to know how they form, where they are, and what influence they are having on our weather. On top of that, there are a couple of other little effects that are really, really worth noting, okay? First of those is the Coriolis effect. If we were not spinning, if the Earth was not spinning, we would just have nice straight winds. They would flow in one really simple direction. It would all be really simple. Because of the Earth's rotation and our oceans as well, our air gets deflected as the Earth spins. And that's what the Coriolis effect describes. It describes the kind of deflecting of our wind from straight lines to these kind of curvy lines. And we need to know this pattern. So here within our Hadley cells, we can see we have what we call our trade winds. So these are typical winds that whip up at the equator and move in this westerly direction. Moving further out in our Ferrel cell, we have winds that move in an easterly direction. So they're moving away from the equator. And then in our northern and southern hemisphere, at our polar cells, we have our lovely high pressure and the air is descending. And this causes wind to be moving outwards, kind of away from the poles. So this is your setup of how the winds look on Earth. And it looks like that because of the Coriolis effect. While we're on the subject of wind, we also have our jet streams. We know about this in the UK because it literally drives our weather. Fast, really, really shallow and narrow streams of air in our troposphere, upper troposphere, which influence our weather. and they essentially carry weather systems which are closer to Earth across the Atlantic towards the UK. It's why in the winter, autumn, winter, early spring, we get our named storms, because the jet stream, it bends and twists and it brings in our weather systems from the Atlantic. Okay. So the jet streams, Coriolis effect, two key terms to make sure you understand. Now, one of the final things with the global energy budget that is really hard to understand is there are seasonal variations. We know this because we look outside at the moment, we have some decently, at the moment, sunny weather. It's taken a bit of a downturn in the past couple of weeks with a bit more rain, which is much needed. But we do have seasonal weather. In the summer, we have warmer, drier. In the winter, we have colder, wetter. And the reason for those seasonal changes you need to know about. So in brief, I've labelled all of the reasons for seasonal variations in our global energy budget and therefore our weather. Okay, so these are the 5 that you need to know about. Latitude, first of all. So the equator is warmer, that we know that, that's where the sun gets its rays. The poles are cooler due to the angle of the sun hitting the Earth. Distance from the sea. Okay, land heats and cools quickly. What that means is we get really big swings in temperatures at our coasts that drives and that moves inland. So inland, you can get a lot more changes in temperatures, while at the sea, it usually warms and cools a bit slower. And so at the sea, you get a more constant, moderate coastal climate, whereas inland it can be a bit more turbulent. Our prevailing winds. So winds bring temperatures from their source. Sea winds cool summers and warm winters in places like Britain. Okay. What that means is our winds are constantly moving, and in summers they can help to cool things down. In winter they can help to warm things up, but they are constantly changing between those two different seasons. Ocean currents. Currents move warm water from the equator towards our poles, and that influences our coastal temperatures beyond what latitudes can predict. So sometimes you wouldn't expect us to have warm, lovely warm coastal temperatures down in Argentina, but actually you can do because of the movement of some of our ocean currents. So again, it's the interchanging relationships between these different factors that can influence our weather. And of course, altitude, mountainous regions compared to low-lying regions, that can have an effect as well. My main piece of advice with this lovely part of the topic is read the notes that we have on Oxbridge. Do your research around ocean currents in particular. It's a really popular exam question. I'll show you some examples at the end of the hour, but yeah, a really, really popular part of the spectrum they like to ask questions on. Fantastic. Right. As a final question for global energy budgets, explain the pattern of solar radiation between the Tropic of Cancer and the Tropic of Capricorn shown in figure 2.1. I've put the mark scheme up there just to have a little think through and jog some memories, and then I'm going to show you a model answer. I'm going to give you 30 seconds to think about it again, but again, just be aware of our command word here, explain. Describe command words mean, okay, well, we've got 2,200 to 2,500 kilowatts per hour meter squared in kind of the western parts of South America. You would be describing what you see. An explain question means give me the geography behind what I'm seeing. So why is the pattern of solar radiation between these two places the way it is? That's what explain means. Give me the geography, the reason behind it. Don't tell me what you see from the figure. That's what we mean by explain. Wonderful. Taking just a few seconds to have a think of your answer for this question. Fantastic. So let's have a look at our answer. Now, one thing I just want to point out before reading this is do just have a little look at this term here, our intertropical convergence zone, our ITCZ. In very short, it's a system that sets up at the equator that takes into account the trade winds and ocean currents and the movement of air and how that influences equatorial climates. So the ITCZ in the notes is just an area that you're not going to get asked about specifically, but it does really influence our weather. So this is one of those that I would always tell students, make sure you understand and can explain, but you're not going to get asked on it specifically. So our answer here is between the Tropic of Cancer and the Tropic of Capricorn, solar radiation is highest near the tropics and lower at the equator. This happens because the sun is directly overhead between these latitudes during the year. This concentrates our energy around the tropics. However, our ITCZ near the equator causes warm, moist air to rise, creating cloud cover that reflects that sunlight and reduces solar radiation reaching the surface. In contrast, the tropics experience clear skies due to descending air in the Hadley cell's high pressure zones, allowing more sunlight to reach the ground. This is why the figure shows darker areas are higher solar radiation around the Tropic of Capricorn and the Tropic of Cancer. Fantastic. Any questions, pop them into the chat. Just to answer that one there, we do live streams fairly often. There's no set timetable at the moment. The next one we are doing is a week today. So next Thursday, the 31st of July, that is our next live stream at 1 p.m. when we will be doing Unit 3, so our rocks and weathering topic. They're all uploaded though onto Oxbridge for you to watch at a later date. Fantastic. Right. That is the worst of the kind of bulk of the topic in there. The rest of the topic, I think, is slightly nicer in what it asks of you, especially 2.4, which is really much better. 2.3 here, though, before we get there, is looking essentially at types of precipitation and moisture within the atmosphere. So this is all about water. It looks at what processes occur, what causes precipitation, and the types of precipitation that we can get. So first of all, it's really important that we know how moisture occurs in our atmosphere and how it changes between different states. So remember our three states, solid, liquid, and gas. Evaporation, that is where we move from a liquid to a gas. For example, water evaporating from a puddle during the day. Condensation is where we turn that gas into a liquid, okay? For example, if you breathe onto a window, it cools down and you can see the water droplets condensing from the water vapor in your lungs. Freezing, this occurs when temperatures fall below 0 degrees and our liquid turns into a solid. Melting above 0 degrees, solid into a liquid. There are two further ones that we need to be aware of in A-level geography. The first of those is sublimation. This occurs when you move directly from a solid to a gas without moving to a liquid first. A good example of this is when snow or ice melts. Yes, it can melt straight away into meltwater, but it can also sublimate directly from solid into gas, which is sometimes why snow and ice can melt so quickly, leading to some flash flooding. The opposite of sublimation is deposition. So this is where a gas turns into a solid. This can occur when dew forms as water on vegetation. So water vapor in the atmosphere, which is gas, can occur through deposition, become frozen onto vegetation. So it essentially misses out the dew stage and goes straight into a hard frost. Sometimes you'll hear about it on BBC in the winter. They'll say freezing air, that's deposition. So 6 terms to really just remind yourself of and be able to explain. You might get a 2-3 mark question saying, explain what the process of sublimation or deposition is. So you do need to know those 2 terms. Fantastic. Right. The next bit is a crash course on why it rains, essentially. So these are our weather processes. This is precipitation. So precipitation is anything that falls from the sky: hail, rain, snow, sleet, whatever it may be. Rain can occur in 3 conditions. The first of those conditions, what we call frontal rainfall. This happens when warm and cold air masses, they meet together. So you get warm, cold coming together. That warm air is lighter and therefore it is forced to rise over the cold air. As it gets higher into the atmosphere, it cools, condenses, and forms rain. Okay. Really common in the UK, we get weather coming across from the Atlantic, warmer air coming from Europe. That Atlantic weather rises above, falls down as rain, and produces pretty cloudy days, pretty wet weather. That's what we get in the UK. You can also get orographic rainfall. Orographic rainfall occurs when moist air is forced to rise above mountains or hills. So it depends on the topography of the land. As that air rises, it does exactly the same thing though. It cools, it condenses, forms rain. This is why Manchester, as the main place that I can think of off the top of my head, is really wet, because you have the Pennines, which act as that hill, and it causes rain to fall. Okay, it's why on one side of the mountain, on Manchester, the Pennines can be really, really wet. On the other side, over towards York, Leeds area, can be much drier. Okay. Same sort of thing in New Zealand, where you have really wet west coast on the South Island, Francis Joseph, Queenstown area, but actually go to Christchurch, somewhere on the east coast, much, much drier because of orographic rainfall. The third one is convectional rainfall, caused by intense heating of the Earth's surface. Often can occur at the equator. Warm air rises, cools really quickly, and forms cumulonimbus clouds. This is what's really common in tropical regions, and to a certain degree in the UK's southeast corner. But this is kind of convectional rainfall is what you think of in the jungle, in the tropics. So those are our 3 kinds of rainfall. All occur because warm air rises, cools, condensates, and falls, but the reason why that happens is different, whether it's meeting warm air, meeting a mountain, or due to extreme heat. There's also really, they just like to throw in more terms for us to learn. There's a nice, tricky concept of what's called radiation cooling. A type of precipitation because fog essentially is a form of low-lying cloud. It's not necessarily a form of precipitation, but it can be caused by similar processes. So the radiation cooling happens on clear, calm nights, mainly during spring and autumn. And it's when the ground cools down really, really quickly once the sun has left it. So the sun's still got strength at that time of the year, but once it's gone, if there's no cloud, that air can cool down very, very quickly. Cold air sinks into low-lying areas of a valley, and as it cools down, it does the same thing. It condensates, it forms water droplets, and they coalesce around what we call condensation nuclei to form fog or dew. Okay. Usually happens after a lovely hot day and you have a lovely clear morning because most of that heat can just escape and it cools down really quickly. It's also partly the reason on a larger scale you get cloud inversions on the top of mountains because that cool air is condensating and forming the clouds because it cooled down really quickly. And that process is what we call radiation cooling. It's the cooling due to radiation, long-wave radiation, leaving at night. We also have our clouds. So clouds are, fog is a form of low-lying cloud. But clouds essentially, they form when that warm air rises, cools, and the water vapor condenses into those droplets. And once that water vapor condenses so much, it will fall as rain. We get 10 types of clouds depending on where they occur in the atmosphere. We can have high clouds like cirrus, cirrostratus, cumulonimbus, cirrocumulus. These are the wispy ones I mentioned earlier. You can have middle clouds, so altocumulus. You can have low clouds, stratus, stratocumulus, nimbostratus, or your vertical clouds. These are your cumulus or cumulonimbus. Now, in all of these terms, nimbus just means contains rain, essentially. And they form over different parts of the Earth due to our atmospheric circulation. So it's where warm air rises. Wherever that occurs, we get these clouds, okay? You don't need to know specifically the different examples, what they look like. It's worth being aware of, but you don't need to know it specifically. You do need to know how clouds form, though, and be able to explain that. So that top bullet point there. And of course, we have our types of precipitation. Hail, it comes from cumulonimbus clouds. Those raindrops freeze while being violently shook up in the upper atmosphere. And once they do so, they fall as hail. Snow, instead, is when frozen water vapor forms ice crystals, happens when it's below freezing in the atmosphere. And we need moisture for that. Heavy snow has to have moisture behind it to fall. It's why Antarctica, the North Pole, they're classed as deserts because they don't get much precipitation because they are so dry. We need water for rain, for snowfall. Dew, we've already talked about, happens on those lovely calm, cool nights. The temperature where the air essentially becomes saturated with water and it turns into water liquid. And we also need to know about humidity. So we've got two ways we describe humidity: absolute, it's the amount of water in the air, and relative, that is the percentage of moisture relative to the maximum that that temperature could hold, noting that warmer air holds more moisture. Fantastic. So our last one here is fog. And I've explained this already. So this is just the fog resulting from radiation cooling. You can also, as well as that, which I have already explained, radiation fog, you can also get what's called advection fog. This is formed when warm, moist air flows across cooler land or sea. So rather than it happening in situ, advection fog happens when that air moves due to a windy climate across a colder surface. When that happens, the same process occurs. It cools down and forms, coalesces, and we get that fog. So that's more something like sea fog in the early morning if you're on the coast. Fantastic. Right. Here again, we've got two questions. Take 30 seconds just to have a little look at these. I've already put the answers up for this one. So this looks at type of precipitation that you need to be able to name and explain how it forms. So just take 30 seconds to have a look at this question. Lovely. So this question looks at fog and it says describe the characteristics of the type of precipitation shown in the photograph above. So the first that we've got is that we've got fog, made of tiny water droplets suspended in the air near the ground, reduces visibility and forms in calm, cool conditions. Characteristics, things like close to the ground, low-lying, wispy, grey, anything like that is characteristic. So that's good to explain. And explain the formation of the type of precipitation shown. Well, at night, the ground cools by radiation, long-wave radiation being emitted back out of space, cools the air above it. When that temperature drops to the dew point, the water vapor condenses. We form those tiny droplets. They form around condensation nuclei, and those droplets form a thick layer of fog near the Earth's surface, usually within depressions, such as within valleys. Right, and on to our final part of this unit. This is my favourite part of the unit. I think this is my sort of geography that I enjoy. So we look at two aspects within the human impact. We look, one, at global warming, and we look also at the effect of urban areas on climate. Now, this final part is where our case study comes in as well. Really important, as always, with A-level geography, to have case study knowledge across as much of the course as possible. Being able to just throw in examples into an 8-mark question can really help boost up your mark. Equally, into 15-mark questions, you cannot score above a 6 in a 15-mark question if you do not include case study information. So it's always really, really important to have. I'm always trying to just give examples of places in the world where this is occurring. For each unit, though, you need a much more in-depth case study. And with the atmosphere and weather unit, that case study is the effect of urban areas on climate. So it says that our case study, students must study an urban area that is affected and how it's affected by temperature, humidity, precipitation, and wind. So within our notes, we have the case study for that you need, and that is your kind of major case study for this unit. So I'm not going to dive into each of these in too much depth because we just don't have the time in this session. What I do want to do is show you the main things that you need to know. Global warming, we need to understand the enhanced greenhouse effect, which I'm going to explain in a second. We also need to understand evidence for global warming, the causes of global warming, and the impacts of global warming. Those are the 4 different areas of global warming we need to be aware of. The first of those is our greenhouse effect. So the most important thing to remember is that if there was no greenhouse effect on Earth, our planet would be at least 30 degrees cooler, which means the average temperature for Britain would be about -18, -19 degrees. Okay, without the greenhouse effect, a lot of species, a lot of things would not be able to survive. The reason I say that fact is because the greenhouse effect is natural. The greenhouse effect describes the incoming shortwave solar radiation from the sun hitting the atmosphere and hitting the Earth's surface. We saw in 2.1 that some of that energy is reflected back into the atmosphere. Some of that energy, though, is absorbed by gases in the atmosphere. It's absorbed by methane, it's absorbed by nitrous oxides, it's absorbed by carbon dioxide. They do exist naturally within our planet. What those gases do is they trap the heat in the atmosphere, causing the atmosphere to warm up. That's what gives us a lovely stable climate. So we need the greenhouse effect to have a normal average temperature. The issue comes when we have human activity enhancing the greenhouse effect. Through human activity, burning of fossil fuels, transport, agriculture. We are putting more emissions, into the atmosphere. We're releasing more CO2 as we burn fossil fuels. We're releasing more methane as we increase our agricultural output. We're releasing more nitrous oxides as transport and cars become more common. The increase in the number of emissions in the atmosphere is therefore higher. They are therefore trapping more heat in the atmosphere, which is leading to global warming. Okay, so make that distinction between the natural greenhouse effect and the enhanced greenhouse effect. Now, beyond that, in this unit, we need to understand the evidence for global warming. So we can look at ice cores, which contain carbon dioxide molecules, and we can see how much carbon dioxide is in each layer of ice, with the oldest ice being furthest underground, and we can see how our CO2 emissions as a species has increased in the last 150 years. We can also look at tree rings. This is what's called dendrochronology, the study of tree rings. And by telling how quickly trees are growing, we can tell how much carbon dioxide is in the atmosphere. And equally, our oceans are a really big store of carbon dioxide. We can study ocean sediments to see how much CO2 there was. We also need to know about causes of global warming, natural causes, things that happen without human activity, so your solar activity or orbital changes, things like precession, eccentricity, all in the notes that we can look at and understand, but also human activity, so transport, deforestation, burning of fossil fuels, and agriculture as the main ones. And then what we're most interested in this unit is the impacts. Global warming, yes, but largely an increase in extreme weather conditions. We've just seen the driest spring on record for the UK, only could have happened due to climate change. So that is one of the biggest impacts we're looking at in this unit. And finally, for the human impact 2.4, we look at our case study. Okay, what we need to know from this case study is how does a human urban environment influence the climate? And we need to look at the effect of temperature, wind, humidity, and precipitation. When you're doing this, concentrate on what's called the urban heat island effect. Cities are warmer than the surrounding countryside. Why is that? The effect of wind, we look at the Venturi effects, transverse currents, the downdraft effect. How do these tall buildings influence the trade winds, the normal winds that we see within the atmosphere? How does that warm air affect the humidity of the region? And how does the urban area affect precipitation? Cities like Calgary in Canada have really, really big storms in the summertime. One of the reasons is because of the city and its interaction with its local environment. Okay, so this is your case study. This is looking at certain urban environments. There are some examples in the notes. Choose that urban environment and study its impact in regards to these four effects. Fantastic. So our final exam question here, I've put up and I will leave up so that you can have a look through. It essentially looks at greenhouse gas emissions, and it gives you two figures, one on methane emissions and one on nitrous oxide emissions in the US in 2018. And the question just asks you to compare them. Really, really easy marks here. We're just using data related to the topic. I've given a model answer there so we can see how to word it. But again, with a compare, you're just describing what you see. With our explain question for C, explain the role of greenhouse gases in global warming, 4-mark question. Here we're wanting to be talking about that enhanced greenhouse effect. the trapping of that long wave emitted radiation and how that then warms the Earth. Fantastic. So just to finish off, I have put in here a couple of long answer questions. These are ones that will come right at the end of the paper, and these are just a couple of examples of questions you might be asked in the exam to help guide where you should do your revision. So for example, with reference to one urban area, describe and explain the effects of human activity on temperature and humidity. That's what we've just been talking about right at the end there. With the aid of examples, assess the extent to which albedo is the most important factor in determining the diurnal energy budget. Explain how ocean currents influence surface temperatures on land. The most significant effect of human activity on urban climates is on humidity. Do you agree with that? Provide examples. Explain how land and sea distribution affects seasonal variations in atmospheric pressure. And with the aid of examples, evaluate the possible causes and atmospheric impacts of the enhanced greenhouse effect. Hopefully just seeing some of those titles gives you a sense of where you need to be focusing some of your revision to look at for this unit. As always, my advice is to take each unit step by step, see how you get on. I am always here for questions. Please do email me. I'm here on the chat. Please do send a message if you have one after this session. This session will be live on the Oxbridge website very soon. And as I said, the next one will be Thursday, the 31st of July at 1 p.m. for Unit 3. So I do hope to see you then. For now, make sure to subscribe to the YouTube channel so you know when more events are coming up. This, as I say, will be available for you to see in the near future, so do go back over and use it with your notes to progress through these units and make sure you are keeping on top of submitting your lovely assignments. Thank you very much for listening. Take care, and I will see you in the next YouTube Live.